In this groundbreaking paper from 1905, Einstein starts from the observation that gases are not the same as electromagnetic waves, because gases are made of particles, whereas electromagnetic waves were seen as something continuous in time. So there was not the idea yet that light could be made of quanta. But there was an article by Planck just a few years earlier which showed that by using oscillators, so discrete quantities, it was possible to derive the correct expression for the spectrum of a black body. So Einstein wanted to try to prove that Planck's point of view was indeed the correct one. In spite of the complete experimental confirmation of the theory, and in this case we are talking about the electromagnetic theory, so Maxwell's equations. If we apply this theory to diffraction, refraction, dispersion, etc., it is conceivable that the theory of light, which operates with continuous spatial functions, may lead to contradictions with experience when it is applied to the phenomena of emission and transformation of light. Einstein thought that the observations associated with blackbody radiation, fluorescence, the production of cathode rays by ultraviolet light, and other related phenomena connected with the emission or transformation of light are more readily understood if one assumes that the energy of light is discontinuously distributed in space. Let's consider the blackbody problem, where we have a cavity with electrons behaving as oscillators. They emit and absorb electromagnetic waves of definite periods. Now, the kinetic theory of gases asserts that the average kinetic energy of an oscillator electron must be equal to the average kinetic energy of a gas molecule. If we separate the motion of an oscillator electron into three components, we find for the average energy E bar that E bar is equal to K Boltzmann, the Boltzmann constant times the temperature. And Einstein writes the Boltzmann constant K as R over N, where R denotes the universal gas constant, whereas N denotes the number of real molecules in a mole. So it's the Avogadro number. The energy E bar is also equal, and we can show that easily, E bar is equal to 2/3 of the average kinetic energy of a free monatomic gas particle. And it is very easy to show this, because if we consider the differential equation of an oscillator, mx double dot plus kx equal to 0, so we have no damping coefficient, the solution x of t will be of the form some amplitude that I will assume for simplicity that is equal to 1 times the cosine of an angular frequency times time plus some shift in the sinusoid, but I'm going to assume for simplicity that we have no shift, so it's just the cosine of omega t. That this is just for the sake of convenience. It's not really a problem if you generalize this expression. But anyway, this equation can also be written as m dx dot dt times dx plus kx dx, and then if you integrate this expression you will get mx dot squared over 2 plus kx squared over 2 equal to a constant, which is the energy E. This is the kinetic energy, whereas this is the potential energy. And if you take the average of these functions, the kinetic energy and the potential energy, in this case you can simply take the average over time. So the average of the kinetic energy will be something like this. It is 1 over t. T is the period in this case, so I should call it in a different manner actually. So maybe I can call it T0 to differentiate it from the kinetic energy T, but as soon as you understand what I mean, it's not a problem. Then you integrate from 0 to T0, and here we have m over 2 x dot squared. So x dot squared will be of the form omega squared sine squared omega t dt, like this. And t0, which is the period, is related to omega, so it's 2 pi divided by omega. And if you do this integration, you will get something like this: m omega squared over 2 times 1/2, which is the result of the integral of sine squared omega t dt, just like that. So you get m omega squared over 4, which is also equal to k over 4, because m omega squared is equal to k. How can you see that? Well, you can see that from substituting this expression into the differential equation, and in order for x of t to satisfy this equation, you must have omega equal to square root of k over m. So omega is square root of k over m, or m omega squared equal to k. So it's as simple as that. And if you take the average of the potential energy, you have, now in this case, you have to integrate k over 2 x squared. So you have x squared of t dt from 0 to t0, and you also have to divide by t0. In this case, you simply have to square the cosine, then you integrate, and you're going to get k over 4 as well. So you get that the kinetic energy, in particular its average, is equal to the average of the potential energy of the oscillator. And since we know that the energy, the average energy E bar of one mode is equal to k Boltzmann T, if you want the total energy, we have to multiply this by 3, because a single oscillator in space has 3 degrees of freedom, and this will be equal to the average kinetic energy plus the average potential energy of the oscillator. But from what we have done above, which is not complete, because in principle you have also other differential equations that contain the other 2 degrees of freedom. So in principle, if you want the total energy, you have to sum all the kinetic energies and all the potential energies, but still you will find that the average kinetic energy is equal to the average potential energy, so this will be twice the average kinetic energy. Therefore, the average kinetic energy is equal to 2/3 E bar, like this, 2/3 K Boltzmann T. This is true for a monatomic gas. According to Planck, regarding the interaction between the oscillators and the radiation present in the cavity, in the black body cavity, Planck derived the condition for the dynamics equilibrium in this case under the supposition that the radiation can be considered a completely random process. We did so in a previous video, and the average energy E bar nu, where in this case this is the average energy per degree of freedom of an oscillator with eigenfrequency nu. This is equal to the speed of light that in this article Einstein calls L. L cubed is the cube of the speed of light. This is divided by 8 pi nu squared times rho nu. And rho nu d nu is the energy per unit volume of that portion of radiation with frequency between nu and nu plus d nu. If the radiation energy of frequency nu is not continually increasing or decreasing, the following equations we must be able to write. So on one side we have E bar, which is R over N T, or K Boltzmann T, which is equal to E bar. This also must be equal to E bar nu, which is equal to L cubed over 8 pi nu squared rho nu, from which we get rho nu equal to R over N 8 pi nu squared over L cubed times the temperature T. This relation is actually not consistent with experimental facts, and this can also be easily ascertained from the fact that if we integrate from 0 to infinity rho nu d nu, since we have nu squared here, we get that this is equal to infinity, which is something nonsensical, because this is not the case when we consider experimental facts. This integral should not be equal to infinity. In fact, Planck was able to solve this problem. Indeed, he found a formula by considering oscillators, by considering the fact that light was quantized. He found that rho nu, and we also found this expression in a previous video, was equal to some constant alpha, nu cubed divided by e to the beta nu over t minus 1, where alpha was found to be approximately 6.10 times 10 to the minus 56, and beta was 4.866 times 10 to the minus 11, something like this. And the constant beta is what we usually denote as h over k, so it is the Planck constant divided by Boltzmann constant. And for small frequencies or large wavelengths, rho nu will be approximately equal to alpha over beta nu squared t from that formula, which is of the same form as that law. Now, these two equations are the same, so we can consider that r over n 8 pi t over L cubed, this should be equal to alpha over beta times t, so we can also cancel t. And from here, we can find n, the Avogadro's number. So n is equal to beta over alpha, and then we have 8 pi r over L cubed. Now, when this calculation is performed, Einstein obtains approximately 6.17 times 10 to the 23. And this result agrees with what was known at that time regarding the Avogadro number. It supports the idea that light is made of quanta. Now, there are some simplifying assumptions that Einstein considered, because in order to derive this number n, which was known at the time, but he wanted to find some kind of connection between particles and light considered as something continuous. Remember that this result is correct for small frequencies.